Welcome to 8.11 Optimization Problems. These are some of the most important and useful applications for derivatives, which is what we've been learning for the last 6 units. So what are optimization problems? Optimization, let's go to Google Translate. Optimization in French, in Spanish, in Vietnamese, in Portuguese, in Chinese. So yeah, optimization. So really, to describe it, I would say that to optimize is to find the best solution to a problem. And in math, what we are really trying to do is find the maximum or minimum points, which is what we've been learning in this unit. For this lesson, we'll investigate, that means to look at examples from business, from medicine, from engineering, and from the AP Calculus test itself. So example 1, business. In business, very often we want to maximize maybe revenue. What is revenue? Well, revenue is how much money you make. So what is revenue? Is the money you make. Businesses want to make more money. So that's why we are maximizing, not minimizing, because we want more. We want the biggest number. Okay. All right. A store has 1,000 phones to sell. The higher the price, the fewer phones they sell. So if they sell a phone at, say, $500, not very many people might want to buy that phone. If they sell the same phone at $300, more people want to buy it. This is modeled by the function n of p is equal to 1,000 minus 2p, where p is the price in dollars and n is the number of phones sold. So the store wants to maximize the revenue, the amount of money they get from selling the phones. At what price should they sell the phones? If they set the price to very high, they can make more money for each phone, but not very many people will buy the phone. If they set the price too low, they're not making enough money for each phone. All right. So we want to maximize revenue. Well, revenue is the amount of money they make. Well, that's going to be equal to how many phones, number of phones they sell, times the price for each phone. If they sell 100 phones at $200 each, then they make $100 times $200, right? The number of phones is given by this function, 1,000 minus 2p, and the price is just p. Distribute, so I get 1,000p minus 2p squared. There you go. So that's the revenue. If I know the price p in dollars, how much they make is r, is 1,000p minus 2p squared. We want to figure out when r is at a maximum. We know that at a maximum point, the derivative is equal to 0, and the derivative of 1,000p is 1,000. The derivative of minus 2p squared is minus 4p. So 1,000 minus 4p is 0. That means that 1,000 equals 4p, and so p equals 250. So we know that, they want to sell, the best price to sell the phone is at $250. That's it. In fact, let's look at the graph. Remember, our function is 1,000 minus 2p times p. We graph it over here. Let's look at our critical point right here. That makes sense. When we sell it at $250, the revenue is $125,000. If the price goes up higher, the revenue actually decreases. If the price is lower than this, the revenue also decreases. So that's the sweet spot. If your business wants to make a lot of money, that's where you want to set the price, 250. How do we get to 125,000? We can plug this back into our revenue formula. So R at 250, that's going to be equal to 1,000 times 250 minus 2 times 250 squared. That's 250,000 minus 2 times 625,000. And that gets us $125,000. So that makes sense. So all we really did was we wrote our function, took the derivative, set it to 0, and found our maximum. Now, of course, this could have been the minimum, but we know from a graph that it is the maximum. If you really want to be sure on the AP test, you can take the second derivative. The second derivative is minus 4, which is always negative. Doesn't matter what p is. So by the second derivative test, we know that p equals 250 is a maximum point. It's a maximum point. Okay. Next, example 2. In medicine, caffeine absorption. When you drink coffee or tea, we know that even when we're really sleepy, we didn't get much sleep. Caffeine, the coffee or the tea, makes us alert. It helps us stay awake. That's because there's caffeine in the medicine. Well, sorry, caffeine in the coffee or tea. When we drink tea or coffee, how much time does it take for caffeine to do its magic? When are we most awake from drinking caffeine? Well, here's a real-life function they actually use in studies in medicine. Here's an actual model we use. C of t is equal to d, which is the dose, over 1 minus beta over alpha, where alpha is the absorption constant. So it's how quickly our body absorbs. Absorption here means to take in. So the higher it is, the faster we take the caffeine in, take in. And beta is the elimination constant. That's how quickly our bodies get rid of the caffeine. So it's d over 1 minus beta over alpha times e to the negative beta t minus e to the negative alpha t. That's the model. For a typical person, alpha is about 2.4 per hour, beta is 0.27 per hour. I got these numbers from a real study. I mean, here's the link. You can find these numbers here. They have the constants in terms of minutes per minute. I converted them to per hour. So at what time t, how long does it take in hours? Is the concentration. That just means how much caffeine is at its maximum. All right. So we have this function. Let's take the derivative of it. We want to take the derivative and set it to 0. So that's c. The derivative is going to be, this is really just one big constant because beta, alpha, and d are all constants. Now we differentiate this thing. We take the first term, that's e to the negative beta t. But chain rule, we have to take the derivative of this, which is negative beta. Okay. Next term, we have minus e to the negative alpha t. Again, chain rule. So a negative alpha comes out in front. Two negatives cancel, we get positive. So that's the derivative. C prime of t is equal to d over 1 minus beta over alpha times negative beta e to the negative beta t plus alpha e to the negative alpha t. When we are at its maximum, the maximum point, we know that the derivative, the rate of change, is 0. It's not going up anymore, but it's not going down yet. We know the graph looks like this. That's the maximum. It's not going up, not going down. So we want to solve this equation. Uh, we can divide both sides by this constant, so it just goes away. So when we solve this equation, we end up with negative beta e negative beta t plus alpha e negative alpha t equals 0. Move this term to the other side and solve. So we can move this term to the right hand side and we end up with this. So we end up with alpha e to the negative alpha t equals beta e to the negative beta t. Okay. Divide both sides by alpha and move the negative beta t term to the other side, and we end up with e to the negative alpha t. We're going to be dividing by e to the negative beta t, but dividing by a negative exponent is just multiplied by a positive exponent. So it's e to the negative alpha t plus beta t is equal to beta over alpha. Take the ln of both sides, the natural log. We know that when we take the ln of e, they cancel because they're inverse operations. So we end up with this. We end up with beta minus alpha t is equal to ln beta over alpha. Okay. And now finally, let's plug in our constants. I'll do it over here. So that means that beta is 0.27 minus alpha, which is 2.4, times t is equal to ln of 0.27 over 2.4. That means that t is ln 0.27 over 2.4 divided by 0.27 minus 2.4. That's the temperature at which caffeine is at its maximum. Let's just copy and paste it in Google so that they'll calculate for us. And we get about 1.026. 1.026. What does that mean? That means that caffeine is at its maximum in the body after about 1 hour. That makes sense. When you drink coffee, about 1 hour later, you feel the most awake. In fact, if we graph this, before this, do this, let me take a screenshot of this. Okay, so let me now I can erase this. So we got 1.026 per hour hours. When we graph this, that's what it looks like. That makes a lot of sense. At the beginning, there's no caffeine in your body. After about 1.026 hours, about 1 hour, you are the most awake. After that, caffeine gradually goes away. After about 4 hours, you have about half as much caffeine as before, and this goes away. So if you want to go to sleep at midnight, it takes about 8 hours for most of them, 9 hours for most of the caffeine to go away. So if you drink coffee at like 4 p.m., 8 is about midnight, 8 hours after 4 p.m. So that's why you probably don't want to drink too much coffee too late in the day. And caffeine is at its maximum at about 1 hour, according to this data. So that's example 2. Next, example 3, engineering. If we have a cannon like this, I'm going to start on the ground. Okay. When I fire a cannonball, the ball goes like this. If I want it to go farther, I might change the angle. And it might go farther. But if the angle is too large, it goes up, but it doesn't go down very far, right? Our question is, we want to know, given that the range, which is how far, so in this problem, the range is this. This is the range. This line. From where we start to where the cannonball lands. The range is given by this function. We know this from physics. We can actually calculate this from the fact that velocity is the derivative of position and acceleration is the derivative of velocity, and that acceleration is g. So r of theta is equal to 2v squared over g times sine theta times cosine theta. R is the range, v is the initial velocity, that's this number, initial speed. Of course, if we make the initial speed bigger, we will go farther, of course. This went too far. Here we go. Initial speed bigger means we go farther. Okay. So let's go back to the beginning. G is the acceleration due to gravity on Earth. Theta is the launch angle. What angle we launch it at. So 25 degrees, 45 degrees, and so forth. The higher it is, the bigger the launch angle. At what launch angle theta should we launch the cannonball if we want to maximize the range R? We want our cannonball to go as far as possible. Alright, okay. So, our function's right here. Again, we take the derivative of our function. So, it's going to be r prime of theta. It's going to be 2v squared, that's just a constant, divided by g, times sine, derivative of sine theta cosine theta. We apply the product rule, so the derivative of the first term, which is cosine theta, times the second term, which is cosine theta again, plus the first term, times the derivative of the second term. The derivative of cosine is negative sine. Okay. So this gives us 2v squared over g times cosine theta squared minus sine theta squared. Okay. We know that at the maximum, we want the derivative to be 0. Because it doesn't matter, the range isn't going up or down anymore, it's at its maximum. Okay. That means that we can divide both sides by 2v squared over g, and that term goes away. So we have, what we really have here is cosine theta squared. Cosine theta squared is equal to sine theta squared. Okay. Well, cosine theta and sine theta are both positive here. So in other words, what we know then is that cosine theta equals sine theta. Where? At what angle is cosine equal to sine? If you're not sure, we can still calculate it this way. Divide both sides by cosine, and we get 1 equals sine theta divided by cosine theta. Of course, sine theta over cosine theta is just tangent theta. If tangent theta is 1, that means that theta equals arctan, the inverse tangent of 1. Plug this into a calculator, and we get theta equals 45 degrees. Arctan of 1 is 0.7 radians, but we want to do it in degrees, and it's 45 degrees. So we know from this calculation that the cannonball goes the farthest when we're at 45 degrees. Let's test this. 25 degrees. Let's go up to 35 degrees. 45 degrees. Yep, it's farther. Well, at 55, it should go down again. Let's see if that's true from our simulation. Yeah. And then at 65 degrees. Yep. As you can see, if we want our cannonball to go really far, we want it to be at 45 degrees. Our calculations make sense. If the initial velocity is 12 meters per second, what is the maximum range? G is about 10 meters per second squared on Earth. So we go back to R. We want 45 degrees. That's going to be 2 times 12 squared, just plugging in the V and the G now. Divide by 10 times sine 45, cosine 45. That's equal to 12 squared is 144, times 2 is 288, divided by 10 is 28.8. Each of these is the square root of 2. That's true for sine 45 and cosine 45. So it's really 28.8 times, oh, sorry, not the square root of 2, but square root of 1/2. So this is really 28.8 times 1/2, which is 14.4 meters. Let's test this. What we're saying is that it's not going to be perfect because we're saying that the acceleration is 10 when it's like closer to like 9.8, 9.81, depending on where you are on Earth. But at 45 degrees, initial speed, our initial in this problem is 12. 12. Let's see how far it goes. We want it to be, we're predicting it to be about 14.4. Let's see if we're right. Perfect, 14.4. Yeah, it's a little bit farther because g is really a little less than 10. Okay. All right, so that's example 3. Let's go to example 4. Example 4, a problem from the AP Calculus test. This is a free response question from actually a long time ago. A tank with a rectangular base and rectangular sides looks like this is to be open at the top. That means there's nothing on top. It is to be constructed so that its width is 4 meters and the volume is 36 meters cubed. If building the tank costs $10 per meter squared for the base and $5 per meter squared for the sides, what is the cost of the least expensive tank? So first of all, let's understand the question. They're saying that the width is 4, so this is 4. This would be the length. This would be the height. Okay. We're told that the volume is length times width times height is equal to 36. Well, the width is 4, so 4L length height is 36, which means that length times height is 9. We'll come back to this in a bit. All right. Well, we want to the least, that's the smallest. Least means the smallest. We want to pay less money for this tank. So we want to minimize. What are we minimizing? How much we pay, the cost. Well, the cost, first let's think about the bottom. So this is the bottom. The cost of the bottom, we're told is $10 times our bottom, which is 4 times length. 10 times 4L. Next, we want the cost of the sides. There are 4 sides. 1, 2, 3, 4. It's $5 times 2 of the sides are 4 times each, and 2 of the sides are length times each height. Okay. So that's really 40L plus 40H plus 10LH, distributing this out. Okay. Well, technically, this is 40H plus 10LH, and then the total cost is going to be 40L plus 40H plus 10LH. That's the total cost. That's the thing we want to minimize. Okay. Now, we have 2 variables here. We want to get rid of one of them. It doesn't matter which one you get rid of. Let's just get rid of height. To get rid of height, well, if length times height is 9, that means that height is 9 over length. So I can plug this in here. So it's 40L plus 40, 9 over L, plus 10, 9 over L times H. Okay. So that means C is really equal to 40L plus 360 over L plus 90. That's the cost, depending on the length. we want to minimize it, so we want the derivative to be equal to 0. So the derivative is going to be, the derivative of 40L is 40. The derivative of derivative of 360 over L, that's 360 times L to the negative 1 power. So that's negative 360 over L squared. The derivative of 90 is 0, so that thing is equal to 0. Okay. This means that 360 over L squared is equal to 40. That means that L squared is equal to 9. We know L is positive. It's a real-life problem. The length can't be negative, so L is equal to 3. So that means that we want the length to be 3 meters. We're not done yet. They're not asking us what the length should be for the least expensive tank. We want the cost. So we plug this back into C. C is the cost. C is, not X, C is 40L, so 40 times 3, plus 40 times 9 over L, 9 over 3, plus, actually let's use this one. This is more simple. Any of them will work. So it's 40 times 3 plus 360 divided by my L, which is 3, plus 90. That's 120 plus 120 plus 90. That's 240 plus 90, 330. So the least expensive tank cost $330. Again, all we did was we figured out the cost. That's the hardest part. That's this function. Take the derivative, set it to 0, solve for L, plug this back in. Okay. So what do these problems have in common? Common means how they are similar. That's what common means. How are these problems the same? Well, for all of these problems, we write a function, and then we take the derivative and set it to 0. Derivative, set it to 0. Derivative, set it to 0. Okay. So we write some function. To optimize, to find the best solution, we want to find the maximum or minimum. So that means the derivative of it's equal to 0. Then we can solve from there using algebra. Okay. That's it for optimization problems.